Good evening. This lecture video is going to be concentrating on the modern atomic theory, starting with the work of Niels Bohr and Erwin Schrodinger, and it will conclude with dealing with electron configurations, orbital notations, and noble gas configurations. As a quick review, we talked about electromagnetic radiation in class today and the fact that it can be pictured in one of two ways. It can either be as a wave or as a stream of individual particles of energy called photons. So we know that light can act as both a wave and as a particle. So to provide a little bit of context, again, the Rutherford model of the atom, which was basically looking like the solar system in essence, where we had that very small dense core, which would be the nucleus, positively charged, but again, no neutrons at this point. And then you had the electrons just kind of flowing around the outside of the nucleus in empty space, like the planets do. So we had one big problem with the Rutherford model of the atom, and something that physics could not explain. And that was simply the fact that if you have this dense center of positive charge in the nucleus, and you have all these negatively charged electrons floating around the outside of it, why didn't they just simply collapse down into the nucleus with that force of attraction? And so you had two competing groups of scientists that were trying to solve this problem, one based on treating the electron as a particle, which was Niels Bohr's group, and then you had the other group which was treating the electron as a wave, which was Erwin Schrödinger's group. So when we look at the Bohr model for the atom, again, he focused on the emission spectra, like you guys did in your flame test lab the other day, the hydrogen emission spectra, to produce a quantum model for the hydrogen atom. Now, when we talk about the Bohr model for the atom, just want to clearly state to begin with that his work was effective for the hydrogen atom, but it could not translate to any other multi-electron atoms within any of our elements. So while his work was useful, it was not the overall correct answer to that question. But what Bohr did say was he came up with this energy level postulate, which basically says that the electrons are going to move in discrete or quantized, meaning that they have to have a specific amount of energy present to be at a specific spot, circular orbits that are around the nucleus, just like the planets are orbiting the sun. Now I've got a little analogy that I'll use in one of the next slides coming up, which is the ball and stairs analogy for the electrons and the energy levels. You can also think about it in terms of, say, the rungs on a ladder, or like little horizontal steps that you would go up. Now, with this ball and stair model or analogy that you would use, you can have a ball bounce up to or drop from one stair to another, but it can never sit halfway in between those two levels. So it can't basically just levitate in between the two steps in midair. It has to be in one spot or the other. So each of the orbits had to have a specific amount of energy that was associated with it, that was indicated as the principal energy level or quantum number for that particular electron. And we can define that principal quantum level or energy level as being a number 1, 2, or 3. You can relate that to the rows on your periodic table. So one of the big things that I would recommend doing is grabbing out your periodic table really quickly so that you can follow along and write some information on that as well. So when we talk about the rows, again, that's the horizontal rows going across the periodic table. There are 7 of them for right now. As soon as we create the next element, it's going to go up to 8. But each orbit, in order to be found in that specific spot, has to have a certain amount of energy present. Now, you may think about the Bohr models in a more traditional way, where you have the nucleus and then you have rings, concentric rings going around it. And each one of those, 1, 2, 3, and 4, and it would go all the way out to 7. I'm going to run out of space here, so just as we go, we eventually have the 7 there. And again, as you get a larger number for n, you have a greater amount of energy that the electron possesses. So let me just write that down here. Higher value for N equals greater energy. Okay. Now, also, when we are dealing with this, we have a couple of important terms that you need to be aware of. The first is what we call the ground states. That is the lowest possible energy state for an electron within the atom. So when we talk about the electron that is found in the hydrogen atom, it would be in the orbit that is closest to the nucleus. And then we have an excited state, and that's when you have the electron that has energy added to it, like you did in the flame test lab, where you added energy from the Bunsen burner, and you cause the electron to jump up to a higher energy level. When it makes that transition, it is a very temporary state, and then it will release that energy back in the form of light that we see in those discrete wavelengths that are released. So every single one of those wavelengths of light correspond to a specific transition between some of these different energy levels. Okay, so when we look at the transition between the energy levels, the atom has to absorb energy first. The electron can then go from a lower energy orbit to a higher energy orbit, and then when the electron is dropping from that higher energy level to the lower energy level, the atom is going to release the energy, and sometimes it will be in the form of visible light. Not all the time, but some of the time it will be in the form of visible light. Okay, so let's take a quick look at the Bohr model for the hydrogen atom. And on the left side, I've given you a diagram that shows the Bohr model for hydrogen, but it also shows you the visible light that is produced during the excitation of a hydrogen atom. So you'll notice we talked about continuous spectra, where we have all the different wavelengths of light that are being produced. But in this case here, this again is what we call an emission spectra, where only specific wavelengths of light are being emitted. And those specific wavelengths of light that are being emitted are based on the energy transitions that are taking place when the atoms have the electron going from the excited state back down to a lower energy level. It doesn't have to be to the ground state, but it just has to be an energy level that's lower in energy than what it began with. So when we look at the hydrogen model here, we'd have the nucleus where that little black dot is, and then I have energy levels 1 through 7. So again, the ground state, that lowest energy state possible for the hydrogen electron, would be found in that orbital 1 around the nucleus. So that would be the ground state, and then anything above that, 2 through 7, would be the excited state for that particular electron. Now, what we see when we excite that hydrogen electron, and we can do it a couple of different ways. We can add the energy in the form of electricity, like you would see with the little emission spectral tubes. You would do it with the flame test, where you had the energy coming from the Bunsen burner, and it could also be manually provided, where if you do the little demonstration with the wintergreen lifesavers, where they say that you can produce a spark in the dark, you're doing that with some type of mechanical power, like with your hands, either crushing it with pliers, throwing it on the ground, whatever it happens to be. But you can have various forms of energy to make that production occur. Now, I want to focus specifically on the diagram on the right, because you'll notice I have the same pattern, violet, blue, green, and red, being shown on both of my diagrams here. You get a little bit more specific with the wavelengths of light that are being produced in the right-hand picture. So if I had a spectral tube of hydrogen gas, which again we'll see in class one day, coming up soon, we would use electricity to provide enough of a energy source to allow the transition from the ground state to an excited state. When that goes through a prism, it will split up the different wavelengths of light that are being produced by those emissions. Some of them we're able to see, some of them we're not. So a lot of times, again, you'll see the colors of the rainbow in some form or fashion, but you could also have ultraviolet X-rays, infrared radiation that's being given off for those transitions as well. And unfortunately for us, we're not able to see that with the naked eye. So when we look at what is taking place here, these discrete lines correspond to specific wavelengths, so they have specific amounts of energy. There are ways that we can calculate the amount of energy that is being produced, which we will go through with you guys in a couple of days. But the energy of the electrons in the atom must also be quantized, so they have to be found as a specific amount of energy. That's what that quantum or quantization is representing. So it has to be a specific amount of energy that's lost or gained by the atom. With Planck, Max Planck was the guy that worked on the hot body radiation and tried to explain using the light as a particle to give an explanation for why we see the certain radiation being given off, which was not what they had theorized it would be, but he postulated that the energy is quantized also, and it would apply to the electrons in the atom. So the big takeaway from this is that each element is going to have its own unique line spectra. So it's kind of like a fingerprint, if you want to think about it like that. Every single element, since it's unique, we can see a sample of an unknown and we could match it up, again, like you guys did in your flame test lab. We can match it up to something that is a known spectra, and then based on that comparison, we could identify the element. And so a lot of times they use these to determine the elements that are present in suns and stars in our galaxies. Okay, so let's more clearly define exactly what we're talking about with the excited and the ground states. So when we talk about the atom, if the atom has an excess of energy in it, we have absorbed energy from an outside source, that is said to be in the excited state. If the atom is in its lowest possible energy state, then it's said to be in the ground state. So again, as we showed on the picture, when that hydrogen atom absorbs energy from the outside source, it will enter the excited state. Now, the specific amount of energy, that quantum of energy, as we said, it has to be a specific amount in order to make that transition take place. You can add energy all day long to it. If it's not the right amount, you're not going to excite it. So the easy analogy that I can give you for something like that is, again, thinking about the stairs or the rungs on a ladder. If you try to step up onto the next step, but you don't raise your foot high enough, nothing is going to happen. You have to have your foot get above that threshold height for the next step in order to make the transition from one step to the next. That's what we're talking about with this quantum of energy, or the photons that are being added to the atom. If it's not a specific amount of energy that's large enough to make the transition from, say, the second energy level to the third energy level, then nothing would happen to the electron. The atom would just re-release the energy that it had temporarily absorbed, and it would wait for a different wavelength and frequency of light to strike it. Now, Bohr's work can extend to other atoms besides hydrogen. You can see here with an excited lithium atom, again, you saw this in the flame test lab, produced a reddish color, but when you have the emission of the photons by a lithium atom, same type of principle. The first thing that has to happen is they must receive a specific amount of energy and become excited. The energy is then released in the form of a photon, and the energy of that photon will correspond exactly to the energy change experienced by the emitting atom. So again, what we mean by the emitting part is, again, it is leaving the atom. So it's being ejected from the atom. So if we look at this picture here, again, basically if I have just a normal lithium atom, that would be like the lithium down here at the bottom. That would again represent the ground state. And then we add some amount of energy specifically to the atom, and that makes it go up into this excited state. So you can kind of think from an analogy standpoint, think about one of your friends going on a sugar rush. They pound a couple of Red Bulls or something For about a half an hour to an hour, they are bouncing off the walls going crazy. Another hour later, you can't wake them up because they've just completely crashed. So that's kind of an easy way to think about this. So the energy goes into the atom, gets it into that crazy excited state. The energy then leaves the atom in the form of a photon, and then it returns back to the lower energy level that it started at. One of the common ways that we represent the electrons within the atom is by using an energy level diagram. You have the energy in the photon corresponding to the energy used by the atom to get to that excited state. You can think about the nucleus being down here at the very bottom, so we could draw a little dashed line to represent the nucleus. This could be the first energy level, which would be that n equals 1, if you remember from the hydrogen diagram. This could be the n equals 2. And so what you'll find is that, again, if I have this electron here at this ground state to begin with, we are going to have some energy that is added into the atom. It will cause the electron to jump up to that higher energy level. So now it again has reached that excited state. It will release that energy in the form of a photon, which we can sometimes see and sometimes can't. And when it makes that transition, it will fall back down to the ground state. So again, we can measure the actual energy that is required to make this transition take place. Within the hydrogen atom, there's a special formula that we use to make that happen, but you guys don't need to worry about that part for now. We can look at the relationship between the energy and the frequency, and as we said, we have a formula, E equals h times nu. Again, remember the nu is the frequency, and h is a constant that we named in honor of Max Planck. So that's Planck's constant, and it is 6.626 times 10 to the negative 34th joules times seconds. So as you can see here, as we expand this energy level diagram out, one of the things that you can see is that we now have multiple levels. So again, still thinking about this being the n equals 1, and that being the n equals 2, n equals 3, n equals 4, and n equals 5. Hopefully you can notice that as we go, the amount of energy again is increasing as we go up away from the nucleus, but you'll notice that the amount of energy that's added, or think about it in terms of the distance between the horizontal lines, is growing smaller as we get further and further away. So what you're seeing is that it's going to require less energy to transition between the n equals 4 and the n equals 5 compared to the n equals 1 and the n equals 2. So even though they're both just transitioning one energy level, the 4 to 5 requires less energy than the 1 to 2. You can also see that if I wanted to transition from the 1 all the way up to the 5, it would require a lot more energy to make that transition take place. So now we're going to shift our focus from Bohr to Erwin Schrodinger. So Schrodinger was the scientist who led the group that was treating the electron as a wave. So treated the electrons as a wave. And so what he did was he set up a set of very complicated mathematical models that he called a wave function, and basically they were the solutions to the answers of where the electrons are found within the atoms. And so instead of having those discrete orbitals or orbits like Bohr was talking about, we had orbitals, very similar in nature but not the same thing. The orbitals are essentially a probability of finding an electron within a certain space around the nucleus that was predicted. That wave mechanical model gives no information about when the electron occupies a certain point in space or how it moves, but it will tell us a general region of space where we can find the electron. So you can see in the little diagram here, there's a little pink area inside. If you want to just kind of, in essence, think about having a Cartesian coordinate system, X, Y, and Z axis going through. The central point right here would essentially be the nucleus, and then the shaded region around the outside is the likelihood of being able to find the electron within a certain point inside of that system. So the big thing here, because we're talking about empty space around the nucleus, they do not have a sharp defined boundary. What we do say is that the diagram that you see on the left, because this one does not happen, the diagram on the left essentially tells us the shape of the region of space around the nucleus where you have a 90% probability of finding the electron. Now, I know you guys have only been in my class for a couple of weeks, but I think you can kind of start to see some patterns that would form and some relationships that you could make. So, for example, you'll see this orbital that we talk about often referred to as an electron cloud in some of your earlier classes. Now, when we talk about this electron cloud, again, it's just a probability chance that we could find it, 90% chance that we could find it within a certain amount of space. So if you think about my classroom and you think about if you were on the outside of my room just happening to walk by the door at any one point in time, if you looked in, where more than likely would you find me during that time? Would I be sitting at my desk? Would I be sitting in front of the room talking to you guys? Would I be wandering around amongst you trying to help you work on problems? Could I be in the lab station? Sure. Those are all areas where I technically could be. I could be, if it's class change, I could be using the restroom, going to grab a drink of water. But if at any one point in time you walk by during the day, more than likely you're going to find me somewhere up near my board writing stuff on it, working with the students out in the middle of the room. That's like my Mr. Anderson cloud. That's that region of space where I will more than likely be found, but it's not a guarantee that I'll be there. So that's kind of the concept behind this orbital or electron cloud. It's that region of space where more than likely we're going to find the electron, but it's not a guarantee. So as I said, with Schrodinger's work, he came up with a set of quantum numbers, 4 quantum numbers, that will basically describe the location where we could possibly find an electron within the atom. Now, as we go through this, I'm going to describe what each of these 4 quantum numbers represent and how we utilize them for determining the position of the electron. Now, we already talked about the first, that principal quantum number, so that is going to indicate the size and the energy of the orbital that's occupied by the electron. So as we said, as the value for n increases, again going from 1 to 7, typically, the orbital becomes larger because, again, we're getting further away from the nucleus, and so the electron is going to spend more time further away from the nucleus than something in a lower energy level. Okay, so big picture relationship right here, very important. The further the electron is from the nucleus, the higher its energy content is. Now, when we talk about those principal energy levels, they can be split into energy sublevels, the S, P, D, and F sublevels. Within those main regions of space, we can break them down into little subsets of regions around the nucleus where there's an increased likelihood to find the electrons. So when you are talking about the sublevels, you can kind of think about them as subdivisions of the main energy level. And each one of these energy sublevels has a shape that's assigned to that electron cloud. So that's going to lead us to our second quantum number. The second quantum number is what we call the angular momentum quantum number. Again, Q dot N dot, that is your angular momentum quantum number. It's also called the orbital quantum number. There are a couple of different terms for it, but it describes the same thing. Now, it is symbolized as a cursive L, just in case you couldn't see that. And it can range anywhere from 0 to the n minus 1. So that first principal quantum number n, whatever its value is, it can range anywhere from 0 to the n minus 1. Each of these values for L correspond to a different shape for the electron clouds. Again, the higher the values also correspond to higher energies. So when we look at these, this is showing us the order in which these sublevels first appear. So in the first energy level, where I have the L value equaling 0, I have just the S sublevel. When I have the P, I have a L value of 1. When I have the D sublevel, I have the L value of 2. And when I have the F sublevel, I have an L value of 3. As we continue to create new elements and we have these electrons getting further away from the nucleus, we're going to start having ground state electrons in the G sublevel, in the H sublevel, so on and so forth. They already are in existence for excited states, but just not for ground state electrons. The shape of those sublevels, the S sublevel, is just a spherical shape. You saw that on the little diagram that I had up just a minute ago. For the P sublevel, and again, I'll show you these in just a moment, that will have a pear shape or a dumbbell shape. You have the D sublevel, they call it diffuse. There are like 5 different shapes for that D sublevel, and then finally you have the F as the fundamental shape, and again you have a very exotic type of shapes for these. A couple of them kind of look like flowers, if you want to help kind of think about that with the F. So now we get to the magnetic quantum number. When we look at the magnetic quantum number, that can be anything that ranges from a negative L to a positive L for that angular momentum quantum number. And this is going to basically tell us how many atomic orbitals there are within that particular sublevel. So this will tell us how many different regions of space have a probability for finding an electron. So when we look at the different sublevels, S, P, D, and F, the number of possible orbitals, again, regions of space where we can find the electrons, in the S sublevel is only 1. So again, because of that value for L being a 0, the magnetic quantum number can only have a value of 0. Each orbital can hold a maximum of 2 electrons. Let me write that down because that is important also. So each orbital can hold a maximum of 2 electrons. So again, as we look at the P sublevel, you can see that down here. This is a P sublevel versus the S sublevel that you can see. So the P has a double pear shape or a dumbbell type of shape, but if you just superimpose each one of those onto their proper axis, they would come together and form just one different shape for that particular model. This one going back behind the board, the one with the bolded line coming out from the board. So 3-dimensional shape, X, Y, and Z axis. My artwork stinks, so I apologize in advance, but that's essentially what we're looking at when you superimpose all 3 of these orbitals over the top of one another. So the P can hold 3 different orbitals, so they can have a value. Since the L value for P is 1, they can have anywhere between a -1, a 0, and a +1. So as a result, 3 different orbitals, 3 times 2 gives me a total of 6 electrons. When I hit the D sublevel, its M value is now equal to 2. So I can have a -2, a -1, a 0, a 1, or a 2. I hope you notice there are 5 different possibilities for these M sub L values. And if you notice, there are 5 possible orbitals for that D sublevel. 5 times 2 gives us a maximum of 10 possible electrons. For the F sublevel, I have 7 possible atomic orbitals, its M value, or L value, excuse me, was 3, so it could range anywhere between -3 and +3. So if you notice, 1, 2, 3, 4, 5, 6, 7 possible orbitals, so I'd have a total of 14 electrons. Now, as I said, if we expand it out to the G sub level, hopefully you kind of notice a pattern, 1, 3, 5, 7. So if I added a G sub level, it would have 9 for its possible orbitals. The M sub L would be anywhere, because this would now get a L value equal to 4. So it could be anywhere between a plus or a -4. So it would now have 9 possible orbits or orbitals, and it would have 18 total electrons. Okay, so that is your magnetic quantum number. And then finally, we have to deal with our spin quantum number. Now, for the spin quantum number, it's symbolized as M sub s. This is when we're talking about the direction of rotation or spin of the electrons within that particular orbital. They're always going to move in opposite directions when they're in the same orbital. So if I have 2 electrons that are found in one orbital, they're going to spin in opposite directions. One will be clockwise, one will be counterclockwise. The values just arbitrarily were given as either a plus or a -1/2. We have 2 electrons in an orbital, that's why it's the 1/2, and then the plus or the minus just to represent the clockwise or the counterclockwise direction. So when we talk about these different quantum numbers, just to give you a quick little analogy for everything, you can think about these quantum numbers kind of being like your address. So if you go on vacation somewhere, say you're out in California, and you meet somebody and they say, "Hey, where are you from?" And you say, "Atlanta." That's a very broad statement. And that person then says, "Oh my gosh, I used to live in Atlanta. What part of Atlanta are you from?" And you say, "Oh, I live in Johns Creek." And so you narrow it down just a little bit further. That's where we're taking, like, going from the principal quantum number down to the angular momentum quantum number. And then that person says, "Oh my gosh, I used to live off of Medlock Bridge in right next to the elementary school." And you say, "Wow, that's where I live." And you could then go down to like a street and then a house number on the street, and you're getting a little bit more specific each time that you give a piece of information. That's what all these quantum numbers are doing. They're giving us a little bit more specific piece of information about exactly where the electron is within the atom. The other way that you can kind of think about it, if that doesn't resonate for you, is if you've ever been to a big sporting event or concert somewhere. So if you go to Mercedes-Benz for a Falcons game, you look on your ticket, it'll tell you enter through gate 3. And that's your broadest piece of information. And then it'll say your seats are located in section 106. And that gives you a little bit more specific piece of information about where you want to enter into the actual stadium itself. Then it'll say your seats are located on row 26. And then it'll say you're found in seats 7 and 8. And so each little piece of information is getting more specific about where your seat location will be within the stadium. That's what the quantum numbers are doing. Okay, so now we're going to start to learn how to apply all of this information. We have something that we call an electron configuration, which is basically an accounting system for where the electrons for a particular element are found around its nucleus. And I've shown you here in this diagram a periodic table. Hopefully you can recognize the basic structure for this periodic table, and then it gives you all the different sub-levels. So here's where you want to have your periodic table out with you to help you out. So you'll notice for each of these different groups, I have the 1s, the 2s, 3s, 4s, 5s, 6s, 7s, but I want you to also notice right here where the helium is located, that is also a 1s electron. So everything that's in the orange, those would all be elements that will end with one of these numbers out in front. Again, the number out in front, when we see the 1s, that number right here is again your value for n. So that is that principal quantum number for that particular electron. So we're just doing a counting system here. We're trying to see how the electrons are distributed around the nucleus for the atom. Now, the one last thing that I'll mention is I always want you guys thinking about the interactions between the different particles. Since I have a bunch of electrons that are found in close proximity to each other, and all these electrons are negatively charged, they're going to have repulsive forces that are acting on them. And then also we have the nucleus with all those protons in it that have a positive charge that are going to be attracting all of those electrons on the outside, trying to pull them in. So it's kind of a counterbalance between the repulsions and the attractions that are occurring between the protons and the electrons with other electrons. Okay, so I have that principal quantum number here going back with the 1. I have the sublevel type. So again, this part here, that's that angular momentum quantum number. That's found here. Now, as we move along in this system, you always want to fill the lowest energy sublevels first before you start adding electrons into an energy level that is higher in energy. So what that means, again, remember we said that the higher the value for n, the greater the amount of energy it possesses. So we want to fill everything in the first row before we start filling things in the third row. So that's our basic order of filling that we're seeing here. We want to go for the 1s and then the 2s, the 2p, 3s, 3p. If you just follow your periodic table, you don't have to sit there and memorize some different order. It makes it much easier to maneuver. So when we're doing these, we're just placing the electrons into the different orbitals. Again, we want to start off with the S sublevel because it's the lowest energy sublevel that we have. We start off with the S sublevel every time that we go to a new energy level. Now, I'm going to do a few examples here to kind of help you out with this. We have a couple of different rules, and I'll just talk about those really quickly before we start, and then I'll explain them along the way as we're doing some of the different example problems. So the first rule that you will find is something that we call the Aufbau principle. And basically that just means building up in German, Aufbau. So we want to place the electrons in the lowest energy orbitals first before we add an electron into a higher energy orbital. The second rule that we talk about is called Hund's rule. And for this one, when we have orbitals of equal energy, so if you remember the P, D, and F sublevels all have more than one orbital. So when we have those orbitals that are equal in energy, we're going to place one electron into each orbital before we add a second electron into any one of those orbitals. So again, I'll explain more about that with a visual diagram here coming up. And then the last one that we have is the Pauli exclusion principle. And this one kind of helps to explain that spin quantum number and why we have the electrons flowing in opposite directions. So with the Pauli exclusion principle, it basically says that no two electrons in the same atom can have the same set of 4 quantum numbers. They can be found on the same energy level, they can be found in the same sublevel, they can even be found in the same orbital, but they cannot have the same spin. So that's the big point of the Pauli exclusion principle. Okay, so let's now start to look at some examples. All right, so we're going to go ahead and look at some of the electron arrangements for some of the atoms on the periodic table. Just a quick reminder, again, that each orbital can hold only 2 electrons. Each s orbital can hold a total of 2 electrons because it has only one orbital. The set of p orbitals, because there are 3 of them, can hold a maximum of 6 electrons. The d, because it has 5, can hold a maximum of 10 electrons. And the F, because it has 7 orbitals, can hold a maximum of 14. So again, the electron configuration, just a little shorthand way to describe the arrangement of the electrons within the atom. So for your writing your electron configurations, the very first thing that you want to do is you want to determine how many electrons are found in a particular element. So when I look at the atomic number, that'll tell me the number of electrons for a neutral atom, and then we can start to look at how those electrons are distributed within the atom. I'm going to draw a Bohr model for a couple of them just to kind of start off with, so you can kind of see how things go. You'll also notice on your periodic table that the number of elements that are found in a particular row, because I'm increasing the atomic number by 1 each time, that's also going to tell me how many electrons are found within a certain energy level. So when we're looking at a generic Bohr model, where I have my nucleus here, and then I have my first energy level, so I'm going to put energy levels down here on the bottom. So I have energy level 1, 2, 3, 4, 5, 6, and 7. So if you look at the first row on your periodic table, all you have is hydrogen and helium. So I have a total of 2 electrons. When I go to the second, starting at lithium, going up to neon, I've got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. There are a total of 8 elements. So I have 8 electrons total. If you notice neon's atomic number, it's atomic number 10. When I go to the third energy level, now I'm going from sodium, Na, up to argon. So in a case like that, I have also another 8 electrons. When I go to the fourth energy level, now things begin to change because I have those middle section of elements that are starting to fill up. And with that, I start off with potassium. And if I count all the way over to krypton, I have a total of 18 electrons. Going into the fifth row, starting again with rubidium, Rb, going all the way over to xenon, I have again a total of 18 electrons. And now we get to the funky nature of how the periodic table looks. If you notice, there's that little block of elements at the very bottom that's pulled out. Those elements are actually part of rows 6 and 7. There's the 18 that are there already, plus the 14 on those bottom rows. So each one would have 32 electrons. So all we're doing with these electron configurations is just starting to fill them out based on these maximum number of electrons. So again, all these here, the max number of electrons in that particular energy level. All right, so let's look at an example problem here. So I'm going to start off by writing the Bohr models for the atoms, or for a couple of the atoms here. So hopefully that will help just a little bit. But again, I want you to notice I put that little picture of the periodic table back out. So again, all we're doing is counting electrons. So the first thing that you need to do is identify what the atomic number is for your element. So when I look at helium, hopefully you guys can find that and notice it's atomic number 2. So that means it has 2 electrons. So if I draw a Bohr model for the helium atom, again, there's my nucleus, there's my first energy level, and it has 2 electrons that are found in it. So when I'm looking at this, again, I tell the position of the electrons in terms of the energy levels by putting the number out in front for the principal quantum number. It tells me again that it is an S sublevel, so I would have S, and I have 1, 2 electrons that are being added in that first row to get to helium. So I'd have 1s2. We place the number of electrons as a superscript to the right of the particular sublevel. So this is what I would have for the electron configuration for helium, just 1s2. So now let's look at oxygen, just a little bit more complicated, but if you look at your periodic table, oxygen is atomic number 8, so it will be found right here. And because of that, I'm going to draw out the Bohr model horizontally here. In the first energy level, I would have 2 electrons, just like helium. And then in the second energy level, I would have 6 electrons. So as I start the counting process, I'm going to go through one by one. I'm starting with the first energy level. It has 2 electrons. So again, we always start with the S sublevel. So I have the 1 for the principal quantum number, the S, and 2 electrons. That now takes care of the hydrogen and the helium electrons closest to the nucleus. So now I can go to the second row. And again, every time I go to a new row, we start with the S sublevel. So I'd have 2s. I have 2 electrons within that sublevel for lithium and beryllium. That would be right here and right here. But I'm not done. I still have 4 electrons left. I've placed 2 of them, but I still have 4 left of those 6 still in that second energy level. So now I go to the next lowest energy sublevel, which is the P sublevel. So I now have a 2p still on the second energy level, but now found in one of those dumbbell or pear-shaped orbitals rather than the spherical orbitals. And then if you notice, I can have a maximum of 6 electrons in the p sublevel, but I only have 4 left. So I have 4. Now, the one nice thing, when you add up your superscripts, 2 plus 2 plus 4, it should always add up to equal your atomic number for a neutral atom. So I'd have 1s2, 2s2, 2p4, 4 oxygen. When we look at magnesium, magnesium is atomic number 12. So I have 12 electrons. If I look at the Bohr model in that first energy level, I would have 2 electrons. In the second energy level, I would have 8. And then in the third, because it's 12 electrons, 2 plus 8 is 10. So I'd have 2 more electrons found in the third energy level. So counting-wise, starting off the same way, I have 1 for the principal quantum number. So I have 1s2. That takes care of those 2 electrons. I now move on to the second energy level. Start off again with the 2s, and it has 2 electrons. Again, lithium and beryllium. Then I have the 2p6. That takes me all the way from boron over here to neon. And then finally, I'm now in the third energy level, because that takes care of those 8. 2 plus 6 is 8. And now I have the third energy level, so I start off with the s sublevel once again, and I have 3s with 2, because magnesium is the second element in the third row. So 2, 4, 10, 12, 12 electrons. Okay. Now, when we go to the iron, we are now hitting this middle section, which we call transition metals. And so now we're going to introduce the D sublevel into this. So if you find iron, it should be element number 26. Should find it right here in that section. So it has 26 electrons. So if I'm looking at a Bohr model, I would have 2 electrons in the first, 8 electrons in the second, 8 electrons in the third, and actually 8 electrons in the fourth. And that's sheer coincidence. It's just the fact that we have 2, 8, 8, and 8 for a total of 26 electrons. If we did any more or any less electrons, we would have an ion for iron. So as we look at my electron configuration in my flowchart, again, same thing. I'm starting off with 1s2. That takes care of those first 2 electrons. I now have to take care of the next 8. So I have 2s with 2. That takes care of 2 of the 8. 2p6. And now that takes care of those. I need to move on to the third energy level. So up here at the top, notice I have the 3s again. Every time we start off with the s sublevel. After the s, notice there's no d's in the third energy level, so I'm going to move over to the 3p. So that is 3p6. So that now takes care of those 8. I now go back over to my next row, and I have the 4s, and that has 2. And now I go to the 3d, and you can literally count 1, 2, 3, 4, 5, 6. So I'd end with 3d6. Now, if you're wondering why it goes down to 3 from the 4, it's just due to the order in which we see these different sublevels. So you notice the first time we see the S is when it's a 1. The first time we see the P is when it's a 2. The first time we see a D is when it's 3. And the first time that we see the F sublevel, it's 4. So it's just going in like chronological order for how many sublevels are present, and that dictates what the number is out in front. So that's why it's 3D instead of 4D, since it's in the fourth row. And then finally we have arsenic, our last one. Arsenic has 33 electrons, so it would be found right here. And so for our Bohr model, with the first energy level, I'd have 2. Second energy level, I'd have 8. Third energy level, I'd have 8. But now this time for the fourth energy level, I would have 15 instead. So as we go through this process, I hope, again, you're starting to see some patterns. First time, it's always 1s2. When I have more than a couple of electrons, I then move to 2s2. And that takes care of these two. I'm now going to 2p6. That takes care of those entire 8. I'm now on the third energy level, so I have the 3 out in front. S sublevel, 2 electrons. And then I have 3p with 6. That takes care of that next set of 8. And then finally, for the 15, I'm in the fourth row. So I have 4s2. Remember, the D sublevel can hold a maximum of 10 electrons. You can also count in the section. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I would have the 3D with 10. That gets me over here. And I have 1, 2, 3 until I reach arsenic. So I would have 4p3. 2 plus 2 plus 6 is 10, plus 2 is 12, 18, 20, 30, 33, 33 electrons. Okay, so that's your electron configuration. Don't worry, it typically takes a couple of class periods for this to all kind of kick in and start to make sense, but we'll just start working our way through them, working some example problems for you to figure it out. We have a second method, which is more of a graphical representation for the electrons that are being filled into these different orbitals rather than the electron configurations, and that's called an orbital notation. So for that orbital notation, you are using a dashed line to represent an individual orbital within a sublevel, and you use an arrow to represent an individual electron. When the orbitals are paired, the second electron is pointing down to represent that opposite spin for that Pauli exclusion principle. So here's where I'm going to kind of illustrate all three of those different rules that we were talking about. So the first thing, when I look at nitrogen, again, I'm going to determine how many electrons I have. So off my periodic table, I notice that I have 7 electrons. So thinking about the Bohr model, again, 2 electrons, and then 5. 2 plus 5 equals 7. So I've got all of my orbitals. So if I were to do this in terms of the electron configuration, again, my first energy level having 2 electrons, I'd have 1s with 2. That now takes care of those. So I move on to my second energy level. So I have 2s2. So I've got 2 of the 5 that have been accounted for, but I have 3 left. So I'd have 2p3. So when we do the orbital notation for these, again, I'm going to make a little graph, kind of like that little energy diagram that we had before. So think about the bottom here as being your nucleus, and then we have an increase in energy as we go up the y-axis. And so again, I'm going to treat all these different orbitals. So I know that the s sublevel has only one orbital, so I'm going to draw one dash, and that's for the 1s, and it has a maximum of 2 electrons. So I'm going to put the 2 electrons, one up and one down. So there's your Pauli exclusion principle. The Aufbau principle, again, I'm filling the 1s sublevel completely before I place an electron into the second s sublevel. That second s sublevel, 2s, has 2 electrons also, so it's going to have a little bit more energy. That's why I'm drawing it up a little bit higher. And it has 2 electrons both paired in the same orbital. When I get to the p sublevel, anytime you get p's, d's, f's, you have to show all of the different orbitals regardless of whether they have electrons found in them. So when I go to the 2p3, again a little bit higher in energy than the 2s, I have the 2p. I'm drawing 3 lines because it has 3 orbitals. Here's where we can go into Hund's rule. So I'm going to place 1 electron into each orbital of equal energy before I would place a second electron into any one of those orbitals. It also says that the spin of the singly occupied orbitals is the same. So I'm going to draw the arrow going in the same direction. So in this case, to satisfy Hund's rule, instead of pairing them up, I'm going to put one electron into each orbital. So I'm just going to circle this part right here, and I'm just going to put, instead of doing the 2p sublevel, like this. And if you remember, we talked about wanting to think about this in terms of those magnetic attractions and repulsions. This is going to increase the repulsion between the electrons. Okay, so we want to do it one each in there. Easy analogy, just think if you have a younger sibling who drives you crazy, you guys will get on each other's nerves if you're in a very confined amount of space, say like your bedroom or your playroom, but you get too annoying, mom comes in, tells you each to go to your own room. By having that increase in distance apart from each other, you typically can kind of neutralize each other and not get on each other's nerves as much. So there's your quick, easy analogy. So let's look at chlorine here. One last one for the orbital notations, and that has 17 electrons. So for the Bohr model, again, first energy level, I would have 2 electrons. Second energy level, I'd have 8 electrons. And then the third energy level, because it has 17 electrons total, it would have 7 electrons. So my electron configuration, again, 1s with 2. That will take care of the first 2. Start off again with the second energy level. So I'd have 2s2. That gets rid of 2 of the 8. So I now have 2p6. That takes care of the 8 in total for second energy level. I now go to the third energy level. So I start with the 3s2, and I have 5 left. 7 minus 2 gives me 5. So I go 3p with 5. Okay, so that is the electron configuration. So the orbital notation, and again, you don't have to show it with the little XY coordinate system, but I just do it to kind of help out a little bit at the beginning. So I would have the 1s with the 2 electrons. I would have 2s with the 2 electrons, 2p. Now we had 6, so I'd have 1, 2, 3, 4, 5, 6. I have 3s with 2, again only one orbital, and then I had the 3p with 5. So I'd have 1, 2, 3. So I've got the Hund's rule coming into play, but now I have no other choice but to start to pair them up. So I'm going to do the down arrow, 4 and 5. So I have one leftover spot where I could add one extra electron in for chlorine. Okay, so that's your orbital notations. And now we have one last shortcut method, which is called a noble gas configuration. So we use these when we have really long electron configurations, and your noble gases, we'll talk about it in one of our upcoming units. Your noble gases are the group 18 elements, so helium, neon, argon, krypton, xenon, radon. Those are the group 18 elements. They have a completed outer shell of electrons, so they cannot add any more electrons into that particular energy level. They'd have to go to a higher energy level. So we do this by writing all the inner shell electrons first as the noble gas in the row above the element, placed in brackets, and then we would just write the outer shell, or what we call the valence electrons configuration for that particular element. So again, I'm going to look at the periodic table here. I have cobalt, that should have 27 electrons, I believe. And so as I look at the electron configuration for this particular element, again, I'm not going to draw out the Bohr model for this one, but I would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then I would have 3d7. And actually, now that I think about it, I am going to do the noble gas, or the Bohr model for cobalt really quickly. so that you guys can kind of see what I'm talking about. So again, I'd have 2 electrons in the first energy level. In the second energy level, I'd have 8. In the third energy level, I'd have 8. And then in the fourth energy level, I would have 9. So when we talk about this, again, the inner shell would be everything except for the very last energy level that has electrons occupying it. So this would be the inner shell electrons. And then this would be the outer shell electrons. Okay, so what we want to do is represent all of the inner shell electrons with a noble gas placed in brackets. So if you notice here for my inner shell, I have a total of 2 plus 8 plus 8, so that's 18 electrons. So if you go to atomic number 18, or you go to the end of row 3, you should notice that as being argon. So when I look at this, everything from here, the 1s2, 2s2, 2p6, 3s2, 3p6, if you notice, that's 2, 4, 10, 12, 18. That's argon. So I could place argon in the brackets, and then I could write the outer shell, which would just be the 4s2 and then the 3d7. So it just provides a shortcut method for us to follow to make this a little bit more efficient and faster process. So if we look at iodine, it is atomic number 53. This will be the very last one that I do for you guys. So when we look at the iodine, again, for its electron configuration, I would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. That would get me to zinc, atomic number 30. I would have, I go back to 4p with 6 now, because I'm in that fourth energy level and that p sublevel. That would get me up to krypton. I then would have 5s2. That would get me to strontium. I then would drop down to 4d10. That would get me to cadmium. And then finally, I would have 5p5. So you can tell if you have the electron configuration, the start of the outer shell is where I have the largest number out in front. So if you notice here, the 5s2, that's the first time I see a 5 out in front. So that tells me that everything to the left of that would be the inner shell, and then everything to the right would be the valence or the outer shell. So if I'm writing the noble gas configuration, I would represent the element that's a noble gas in row 4, which happens to be krypton. Again, krypton's atomic number is 36. 2 plus 2 is 4, plus 6 is 10, 12, 18, 20, 30, 36, getting to the 4p6. So I've got all of that represented by the krypton, and then I could just add 5s2, 4d10, and then 5p5 to that. So you can still count your number of electrons. I've got 36 for krypton, plus 2, 38, plus 10, 48, plus 5, 53. So that gives me all the different electrons in the atom of iodine. So you can use the noble gas configuration only when asked for. If you're not specifically told to write the noble gas configuration, then do the electron configuration instead. So I apologize, I know this was a long video, but wanted to get all the information to you. So I am shutting it down for tonight. We'll do some practice problems together, and then we'll add on just a couple of other little tidbits to this so that you can continue to apply this to your periodic table. Have a great evening, and I will see you all tomorrow.